Hi guys, again, now look at these two diagrams, because this is what I was saying all the time with, your index finger pointing in one direction and your hand pointing at the other one. Let's look at this case, because this is another way to write the magnetic force, but this is the one we're using right now. Your index pointing in the direction of the velocity, the middle finger in the direction of the magnetic field, and the thumb the force. So you always will have your hand like that, and the only thing you have to do is put the vector velocity, index finger pointing in the direction of vector velocity, then accommodate where is the magnetic field, and then your thumb is going to be stuck there, and it will tell you if it's up or down or whatever it is. Okay. Oh, there's one thing interesting. If look at this, guys, if the vector velocity is parallel to the magnetic field, there's no force. F magnetic field is going to be equal to 0. The only way it works is V is perpendicular, right? Or it has certain angle between them. But if it is actually parallel, if they go in the same direction, or anti-parallel, is 0. There's no magnetic force. Okay, so now let's go to the next slide. Okay, so let's look at this case. Motion of a charged particle in a uniform magnetic field. Now look at this particle. They say here, consider a particle moving in the external magnetic field with its velocity perpendicular to the field. Okay, yes, the velocity is perpendicular to the field. The field goes inside the screen or the screen of your computer. The direction of the velocity is perpendicular and is moving along the circle. And look at the direction of the magnetic force by using the right hand rule, always pointing toward the center. Doesn't this look like something you've seen before? Yeah, it looks like you can compare this magnetic force with centripetal acceleration, in which this one is going to be n v squared divided by r. Right, because it's moving in circle and the force is always pointing out in the to the center, so it looks something like that. And if you know the equation of magnetic force, which we know is going to be what? Q B is magnitude, equal to n v squared divided by r. If you cancel here one of the v's, you will have QB is equal to, sorry about that, QB is equal to, we put it here, is equal to NB divided by R. And you can solve here for R, you can solve here for the velocity, you can here solve for the charge. And if we look at the next slide, look at this. They did the same thing, right? Using Newton's second law, we can equate the magnetic field to the centripetal force. What we did. Centripetal force is mv squared divided by r equal to qvb, the magnitude of the magnetic force, and solving for, let's say, r, because you want to calculate the radius of this one. Here you got the equation where r is proportional to the linear momentum of the particle, which is mv, and inversely proportional to the magnetic field and the charge, which is qb. And this actually gives us an equation, an interesting equation. If you write here this, send r here, or divide by r, you get v divided by r. That's actually angular frequency, and that will give you something called the cyclotron frequency. Yeah. Oh, here it is. The angular speed of the particle is omega, which is angular frequency, equal to velocity divided by r. If you're solving here for Vr, which is qb divided by n, and this is known as the cyclotron frequency. Great. And actually, now if we have the angular frequency, you can calculate his period, which is the next equation, I think. There is. Then the period of this motion, t, is going to be equal to 2 pi r divided by the speed, or r divided by v is angular frequency, or, now going back, you remember the equation, v equal to qm, it's going to be m divided by qb, 2 pi n divided by qb. Okay. This is, well, here says the angular speed of a particle and a period of a circular motion do not depend on the translational speed of the particle or the radius of the orbit for a given particle in a giving uniform magnetic field. Well, okay, we can see that in the equation. So let's go here. If a charge, well, the next statement here. Okay, if a charge moves along a magnetic field at some arbitrary angle with respect to the field, its path in the helix is going to look something like this. And inside this helix, the magnetic field is going to look like some kind of uniform. You actually can calculate the velocity by using like the magnitude of velocity. You know, there's component in x and component in y. We already discussed this in where we're doing vectors and magnitude of forces. And now if we're going to look at another example, let's see, look at another example. Here we have example. A proton moving in a perpendicular magnetic field. A proton is moving in a circular orbit of a radius of 14 centimeters in a uniform magnetic field of 0.35 Tesla, perpendicular to the velocity of the proton. Solve for the speed. So here we have the equation, right? Here we have the equation for V. We solve for B. We substitute here the charge, which is an electron, 1.6 10 to the minus 19. I mean, it says proton, so it's positive. We don't need to use absolute value. Because for calculating this thing we will need the magnitude, so the positive quantity. Then we multiply by the magnetic field, which is 0.35 Tesla. Then we multiply by the radius, which is given in centimeters, but remember MKA, so you have to use the units in meters, kilograms, and seconds. In this case is 0.14 meters, and then divided by the mass of a proton, which is 1.67 10 to the minus 27 kilograms. And here's the velocity of that particle, that proton moving along that magnetic field in a circular orbit. Okay. The next class or next lesson is going to be about magnetic forces between parallel conductors. And I think it's behind the idea. The idea behind this thing is those known as maglev or something. Those trains that goes gazillions kilometers per hour, like 500 kilometers per hour or something. We're going to discuss that in a second. Next slide. Take care, guys.